So it's 4 for question number 37. So this one right here, log base 3. Is that right?
Yeah, that one.
Okay. Yeah. It says expanding logarithmic expressions. Use the laws of logarithms to expand this expression. Okay, so let's make some space over here. Seven says expand log base 3 of root 3x to the 5th power over y. Okay, so expand log base 3 of, and then we have this inside our root. So I'm just going to use a little bit of algebra to manipulate this a little bit. And also the first rule I want to take advantage of is this one. So in general, we have that log base a of anything, say x over y, like this, a division of something in the argument is equal to log base a. I need more space. And I probably shouldn't be using x and y. So let's try it again. Log base a of, I don't know, about w divided by q, whatever this is, some sort of division, is equivalent to log base a of w minus log base a of q. Right? So that's one of our rules. Another important rule, number 2, is that log base a of w times q, if there's a multiplication inside the argument of the log function, we can rewrite it as the summation of two different logs, w plus log base a of q. And then finally, the third rule we want to use is that log base a of w raised to the power of, I don't know, d, e, f, g, h, I don't know, n. Let's use n. Log base a of w raised to the nth power as an exponent can be rewritten as a multiplication of n times log base a of w. Okay, so these are the three main rules that we want to use to expand or contract logarithmic expressions, such as this one. Okay, all right, so first we have this giant division, so we're going to use this first rule to separate this as log base 3 of root 3x to the 5th power minus log base 3 of y, right, using that rule. Then I'm going to rewrite this, using a little bit of our algebra skills, as 3x to the 5th power, and then that whole thing is being raised to the 1/2 power, right? That's another way to look at this root right here, minus log base 3 of y. And now, using this rule, we can bring that exponent out in front, like a linear factor, and have 1/2 times log base 3 of 3 times x to the 5th minus log base 3 of y. Then we can use the rule where we have a multiplication inside the argument to separate these two. make sure you bring this along since it's part of the whole thing. So it's 1/2 times, and now this log base 3 of this product gets rewritten as log base 3 of 3 plus log base 3 of x to the 5th power, close that up, minus log base 3 of y. Okay, by definition, log base 3 of 3, that's just going to be equal to 1. Right? This equals something such that, remember this little circle, it must be true that this to the power of this equals that. Right? So 3 to what power equals to 3? Well, it's got to be a 1. Right? So this whole thing just becomes 1. And now this guy, well, we can use this rule one more time. We can move the exponent out in front. We could not do it here. Notice that we cannot do it here because this 5 only applies to the x. It does not apply to the 3, so we can't move the 5 out in front. But here, now we've written it down, so we've written it gotten to a point where we have an exponential number in here, so we can move the power out in front. Okay, so then I'm running out of space, so I'm just going to jump to the final answer here. This is going to be equal to 1/2 times 1 plus 1/2 times 5 log base 3 of x minus log base 3 of y. Right, so 1/2 times 1 gives me this. 1/2 times 5 log base 3 of x from there, and then this guy. So I guess you don't really need this, so let's just rewrite it in our final step as 1/2 plus 5/2 log base 3 of x minus log base 3 of y. Okay, so if you just joined us, it's section 4.4, question number 37, and the instructions were just to expand this log statement expression by using our properties of logs. And so we get to that. Any questions? No? Good. No questions. Okay, anything else from homework?
Chapter 6.3, number 47.
6347. Okay. Page. 6.3, number 47. Six point three, number 47. Here it is. This one. Sine of theta equals to -4/5 theta in quadrant 4. Find the values of the trigonometric functions of theta from the given information. Okay, so let's see. Let me copy some of that down. So we have sine of theta equals to negative. So sine of theta equals -4/5. And we know that theta is in quadrant 4. And it just says find the values of the trigonometric functions of theta from the information. So they want to find sine, cosine, tangent, and then from there you can find all the others. Okay, so to solve this, Okay, so to solve this, we're going to consider, first of all, ignoring the negatives for a second, right? So momentarily consider just a triangle. Now it's got to be a right triangle because we have this sine of theta. Remember, sine of theta, that whole thing, that whole property only applies to right triangles. So I have to have this image. I have a right triangle there, and then theta there. And there's some variations, of course, that you can take, but no matter what you do, you're going to end up with a right triangle, no matter how you draw it, and then one of the other angles is theta. Good? Okay, so consider this one where it's not attached to a Cartesian coordinate system. In fact, you could tilt this if you wanted and just say, okay, well, let me draw it this way. Maybe it's like this. Right? I'm not attaching it to any coordinate system for a second. It's just an arbitrary triangle. It's a right triangle. There's a theta there. And I'm thinking about the case where this is, in fact, since it's not that necessarily that one right there, I'm just going to call it theta hat. So in this arbitrary case, I'm considering sine of theta hat equal to positive 4/5. Okay, well, that's going to be 4 over here and 5 over there, which means that we can find this missing side, A. Okay, so that's sort of an arbitrary triangle in general. And then, okay, we can think about the one that's in quadrant 1. We can tie everything to quadrant 1 where everything is positive and pretty. It's simple, right? Everything is much simpler in quadrant 1. So let's think about this triangle. So I'm just moving that one over here. It's still not the angle they gave me. It's just something in quadrant 1 where everything works out nicely. And I have this missing side over here. Now I could call it A, B, whatever. Again, we use X a lot. So if you look at solutions somewhere, it probably will have X on it. But don't let that confuse you from this interpretation of it. I mean, the X is the X-axis, whereas here X is this missing length of this triangle here. Now it is nice to label it as X because it's on the X-axis and we're starting at 0, so its length would be the same value as the value on the X-axis. So that's why we like labeling it X. But it also causes some confusion. Anyway, so let's say that guy there. Okay, we know that it must be true that x squared plus 4 squared must be equal to 5 squared, right? Pythagorean theorem. So x squared plus 16 equals 25, which means x squared equals 9, which means x equals to plus or minus 3. And then clearly we're talking about positive 3. Right, so we're going to ignore the negative. Ignore the negative. And so this equals to positive 3. Okay, in general, whenever they give you something like this to solve, just think of it in quadrant 1. What is it in quadrant 1? What can we find about it in quadrant 1? And then move it over to the values that they give you. Now, if this part was not there, we have to think about what quadrants is sine negative. So remember that in the Cartesian coordinate system, sine is opposite over hypotenuse. The hypotenuse is always positive. So in order for sine to be negative, the opposite side has to be the negative one. And there's 2 quadrants where that can happen. So that can either happen in quadrants, just sort of arbitrarily, we have a triangle here, like this. Here's one way that you draw a triangle, and another one is over there. Right, so this is always the hypotenuse. We have to use the letter R in this case for the hypotenuse. That part's always positive. So if this is theta there, or this is theta there, then opposite over hypotenuse, or opposite over hypotenuse, these are the 2 ways that this could be true. However, they further emphasized the correct one by saying that it was in quadrant 4. So it matches that it's got to be this one. Good? Okay, so I've way overkilled it here. You don't have to do everything I'm doing. I'm just showing you how there's a whole lot of information that can come from different angles here to give you the thing you need. And you know what? I need to make more space, and I don't need that much. Okay, so there's this triangle. It looks like this and goes up that way. And then there's an angle here. Opposite has to be -4 over 5. And then this one is clearly 3. Right, for the same reason as this over here. Good. So now we have an angle here such that, call it theta, angle sine of theta here, that gives you that opposite over hypotenuse is this. And now that we've created our triangle, we can figure out all the other trigonometric functions based on that. Good. So we can just go over them from here. Cosine of theta must be equal to 3/5, adjacent over hypotenuse. And tangent of theta must be opposite over adjacent, -4/5. 4/3. Good. Cosecant of theta is going to be equal to 5 over -4, so -4/5. And secant of theta is equal to 5/3. And cotangent of theta is equal to -3/4. Good.
Thank you.
Welcome. Okay, so we gotta piece these things together, create a triangle. It's often good to go back to quadrant 1 where everything is positive and pretty, and then piece together the other pieces, other pieces of information that are provided for you to think about what quadrant is the one they're giving you, what quadrant is it in, and sometimes more than one quadrant might satisfy the answer, so you might have more than one solution to it. Okay, any other questions?
Hello.
Yes, can you hear me?
Yeah, by any chance, would you mind doing 4.5, number 71?
4, 5, 71.
Thank you.
Sure. 4.5, number 71, you said? 4, 5, 71.
Yes, please.
4, 5, 71. Chapter 4, 4, 4, 4, 4, 5, 4, 5, 4, 5, number 71. Right here. Solve equations graphically using a device. This one, number 71.
Yes, please.
Good. Okay, it's a great question, and it allows us the opportunity to solve this using technology. Right. That's what it wants us to do. So let me copy it. Number 71 says we have x to the 3rd power minus x equals to log of x plus 1. Okay, so very important to note that this is a calculator or technology question, right? Your book identifies all of those with this little calculator symbol. So make sure that when you see those, that you're using technology to solve them, because in most cases, it's not like, oh, if you were good enough in math, you can do it by hand. You don't need a calculator. Like, you need a calculator. These are really difficult to solve in most cases. There's some rare ones where you can kind of go, oh, forget it, I can just figure it out, and it's doable. But they give you good, difficult, challenging questions in these ones that indicate use technology. So use technology. Okay, so here is another opportunity to use one of the most useful tricks you'll learn or that we practice in this class. Well, useful for other math classes or other science classes, I guess. Any rate, so what we're going to do is, in order to solve this equation, we're going to think of this as one function here on the left and then another function here on the right. Good. We're going to graph both equations and then we're going to see where they intersect. The intersection of the two is our solution. As an example real quick, let's consider this for a second. Let's say I just wanted to solve, what is x plus 3? When is x plus 3 equal to 8? Simple enough question. Sure, the answer is 5. Okay, we could do it. Or we can do this same strategy of letting this be a function and letting this be a function. If we let this be a function, then we end up with an equation, a function that looks like this, f of x equals to x plus 3, right? And if we graph this, it's a linear equation, slope 1, y-intercept of 3. So if we graph it, it'll look like this. We have y, we have x. It gives us all the outputs for various inputs, right? So this will have a slope of 1, y-intercept of 3. Let's use blue. It'll end up looking something like this. Right, where it goes through there at -3, and it goes through there, 0 gives you +3. And then it has a slope of 1, so then it just starts climbing where this is the number 1, 4. And there you go. So this is this equation right there. And now if we want to figure out the solution here, all we have to do is figure out where it intercepts the line y equals to 8. So let me make a little bit more, let me erase this here and make a little more space. Y. This one. So now if I take this line, let's put it, say, up here. I know it's not up to scale, but you get the point. So here's the equation y equals to 8, right? In this case, it's just a straight line. So the place where these two functions will intersect will be the solution to this, right? It'll be a place where the input to this function equals 8, right? This side will equal that side. And so here will be a 5, and this will come up here, and this will be 8. So 5, 8 will be this point right in there, and it'll be the solution to this. The x-coordinate of our intercept point will be the solution. Good. Okay, so in that same spirit, we're going to do the same thing over here. By letting this be one function, we'll end up with some function f of x equals to x cubed minus x. The right side is another function. Let's call that function g. G of x will be equal to log of x plus 1. Okay, without drawing it, let me just kind of roughly sketch what this is going to be. This is going to be some function. I don't know what it does. Maybe it goes like this. I don't know. Maybe it goes like that. Say it does that. And then here is this other log function that's going to go there, and maybe, whatever. Let's say it just does that. Then there will be a couple of places here and here and here. The way I've drawn it. Again, I haven't drawn it yet, so I'm not really sure what the answer is. But if they look like this, then these three places will be intersect points. The x-coordinate for both functions gives you the same output. So we'll find a place where the input x gives you the same output on both sides, therefore they equal each other. Okay, as a general concept, is it okay? Before we actually graph it? Okay, so let's actually graph it and see what it looks like. Okay, so then this is where we use technology, because otherwise it's kind of hard to do it. So I'm going to use Desmos first, and then we can go back and check with our calculator to see how we would do it there. So on one of them, we're going to say f of x equals to x to the third power minus x. Okay, so here is what it looks like, this little wiggly thing there. And then the other one was g of x equals to log. Oops, I need to. So if you're using Desmos, you have to go down here to get the log. And under functions, and then miscellaneous, and there's log. And it was just log base 10. So log of x plus 1. Okay, zoom in a little bit. Okay, so it looks like there's going to be two solutions. There's one there, and there's one there. Good. So here is the left-hand side of my equation, and then here's the right-hand side of my equation, and they have these two ordered pairs in common. So the x coordinates are going to be my solutions. Good. So 0, 0, and 1.136. Okay, so going back over here. Wait. Looks like this came up. Oops. This came up and down through there, and then up that way, I think, something like that. And then the other one came up, let's put it in blue. The other one came up this way from over here and crossed there and then went that way, like this. So this one is g of x equal to log of x plus 1, whereas this one over here, this one is f, oops, f of x equals to x cubed minus x is this one. Okay, and so clearly they have these 2 points in common. This point right in there, 0, 0, and this point right in there, which was 1.136, 0.33, is that point in there. Double check. It's 1136 and 0.33, right? 1136 and 0.33, 00. Okay, roughly speaking, there you go. Okay, so from interpretation of these intersect points, at point 0, 0, it must mean that f of 0 equals 0, right? And it also must mean that g of 0 equals 0. So if we go back to our definitions of f of x and g of x, it must mean that blank cubed minus blank equals 0 whenever the input was 0. Okay, that's obvious. 0 cubed minus 0 equals to 0, true. And then it must also mean that log base 10 of blank, which in this case is 0, plus 1 equals to 0. And yeah, that's true. Log of 1 equals 0. Log of 1 does equal to 0. Okay, it checks out, and they both outputs equal to 0, therefore they must be equal to each other. Okay, that one was maybe a little too obvious, all those zeros running around. Let's check the other one. At 1.136, 0.36, comma 0.33, it must mean that blank cubed minus blank equals the output of 0.33, right? It must mean that if I plug in a 1.136 into this, that the output is 0.33. And we can check that with our calculator. Okay, it must also mean that the other side is also going to be true. Log of blank plus 1 equals 0.33. Right, where that blank is the 1.136. And again, we can check with our calculator. And since they both equal 0.333, I can set this side equal to that side, right? Since they both equal 0.33, it must also then be true that that blank cubed minus blank is equal to log of blank plus 1. Good. Where that blank is this 1.136, 1.136, 1.136. And why is this equal? Because this side was equal to 0.33 and this side was equal to 0.33. Therefore, they must be equal to each other. They both give you an output of 0.33. But if we compare that back to the original question, way up here, solving this, we've solved it. We figured out the blank that goes into all of these places to make a true statement. Right? The original question was given like this. Find x such that x cubed minus x equals to log of x plus 1. Well, we found it. The x is this guy. The x is to 1.136. It's the same as this, but I think with all those zeros running around, it seems a little weird. But we also get another answer from here that x equals to 0. Okay, so this style of solving things graphically will indicate for you that the x coordinate is the solution. Not the ordered pair, the x coordinates are the solutions for the original statement. Is that okay?
Cool.
You good?
Awesome. Thank you, sir. Oh, Professor.
No problem. Yeah, this makes it a really it's a really useful way of solving really complicated equations or inequalities in this manner. Just graph them, see where they intersect, and the intersection makes it true. Now, the other thing you could do is move things to one side and set it equal to 0, and then you'd have one big ugly equation, and then you'd want to know when does that big ugly equation equal to 0, right? That's the other thing you could do. And again, you could use graphs to do that. So if we move it all to one side, let's call it h of x. Oops. H of x. That's equal to x to the third power, minus x minus, right? If we move it all to the other side, it's going to have minus this log thing. Minus, copy, B. So we have that. So now we erase that. And now we want to know when does this whole ugly thing equal 0, right? If we move it over to one side, we set it equal to 0 and solve for it. And here they are. It equals 0 there, and it equals 0 there. Same answers. 1.136 and 0. The x coordinates are our solutions. Good?
Pretty cool.
Yeah. Okay, let's do it with our TI-84, since you won't always have Desmos and you got to learn how to maneuver through the calculator. Same idea, you just have to learn this technology and where the buttons are, but it's not bad. Okay, so we're going to go over to y equals, and you got to type in your equation. So let's type in x to the third power, x to the power of 3 minus x. If you have an older version of it, you got to be careful with all these exponents, so wrap it around parentheses and stuff. Then we got log base 10 of x plus 1. Oops, I mean next one. So x plus 1. Okay. Next, go over to your window and see if it's an appropriate window, and see how this is very inappropriate for what I'm doing. X minimum of 50 to 300. This isn't going to work. If you're not really sure where the window should be, then just start off with a standard window of -10 to 10. Right, that's just kind of by default what you should start off with, and then take it from there. See if you feel that you've gotten the entire image from there. There's one. Okay, so you can kind of get a sense that, oh, this is way too big. We need to focus right in there. And so I don't need to go that far out, maybe -2, +3, something like that. Let's go from -2 to +3, and then -2 to +3. I don't know, just kind of, again, guessing and checking to see how the graph looks. So there we go. Okay, that one, it looks like it's 0, 0, but you can't be certain by just looking at it, right? Because it might be that the answer is 0.012, and you can't tell that from here. So you got to verify by using the intersect function. So you got to go right here where it says calculate. You're going to hit second, calculate. Intersect is the 5th button down, intersect. And then you're going to select the first curve, select the second curve, and then you're going to guess. You're going to go right over there and guess. Hit enter. Okay, now we know that the intersection really is 0, 0, and we know the x coordinate is our solution, not the ordered pair. Okay, do it again. Second, calculate the 5th option, intersection. So we're going to go over to the other button, the other intersection. So hit enter to select the first curve, enter to select the second curve, and then guess somewhere near there, enter, and then we get that exact answer. So again, the x coordinate is our solution. Good. Any questions on this then? All right, any other questions on anything?
Were you around when slide rules were a thing? No.
Wow.
'Cause my mom told me about that, and it seemed like
I was in the transitional period in that calculators were just really expensive. So we had these, a TI-83 was my first calculator in probably the 9th or 10th grade. We were really poor, so we couldn't afford what felt like a $300-400 calculator at the time. It was probably the same price, but in 1992 money, it felt extra expensive. So I remember we went down to a pawn shop and we found one, and it was one. Not only was it the 83 edition, but it was one of the earlier, like it really super square and like really, it didn't really have all the newer functionality, but it was good enough. And it worked great. You gotta give it to them. They made really, really durable calculators. I don't know about the newer ones. They seem a little too plasticky, but who knows? But I guess maybe they're okay. They seem pretty durable, and I think we paid like $50 for it, I think. And that thing lasted me for a pretty long time. I'm pretty sure I have it still somewhere. But at any rate, so they were just expensive, and so it was still one of those things where some people still had slide rulers because they couldn't afford the calculator, kind of thing. Like, it wasn't fair for the teacher to say, everybody get your calculator out, because some people couldn't afford one, and the school definitely didn't provide them for us. So yeah, but I never learned to use one myself. You just, I don't know, slide things. And the other thing is, our culture doesn't really embrace knowledge and being smart, particularly at my high school. So anybody with a slide ruler just kind of got beat up and attacked all the time. So it was kind of dangerous to be walking around with a slide ruler or with books. you know, the cool thing to do was to walk around and like not carry anything because you didn't care. Like the nerds had the books. I have nothing. People didn't walk around without even like a pencil. Like you just walked around school with nothing. Are you even in school? What are you doing?
Yeah.
It's fun. It's cool. All right. Enjoy life. Anyway. So anyway, back to this. Any questions on anything? You feeling pretty good about being ready for tomorrow's tests? No other questions? Good. Okay, so in that case, yesterday we left off with talking about 6.4, and I wanted to kind of look at a couple more of those examples. So where am I now? This is 5. Six one, and this is 6.3. Okay, I wanted to take another look at these kinds of examples. Did anybody get a chance to look at the homework, and are there any questions on any of these guys, or should I just kind of pick one and go with it? Okay, I'll pick one. How about 32? 32 has cosecant of cosine inverse of 7/25. So let's do that one. This is 6.4, number 32. And we have cosecant of cosine inverse of 7/25. Okay, so what you want to do with these is, again, first of all, recognize that when we have cosine of theta equal to whatever, y, then we're inputting in an angle. This is some angle, and the output to a cosine is a decimal between -1 and 1, right? But this is an inverse function, so it goes backwards. It inputs a decimal, cosine inverse of y. Well, let's use a different letter. Inverse of x equals alpha, and it's going to be something where this input here is a decimal. You input a decimal between -1 and 1, and the output is going to be an angle. Now, we had to restrict the domain of the cosine function in order for this to work. And for cosine, we restrict it to be an angle between 0 and 180 degrees. For sine and for tangent, we restrict it to be an angle between -90 and +90 degrees. Good? Right? And so this is true if and only if, right? This is true if and only if, and sort of by definition, it must be true that cosine of this alpha equals to the x. Good. It's the answer to this cosine inverse will be an angle such that cosine of that angle equals the x. Good. Any questions? And then, of course, the restriction in radians is going to go from 0 to pi. Questions? No, we're good. Okay, so when you're given this, we can do like a quick little substitution. Right? This is an angle. So from here, I can tell that cosine inverse of 7 over 25 will be equal to some value of sigma. It equals to some angle, right? And it's going to be some angle such that cosine of that angle, cosine of that sigma, will be equal to 7 over 25. Good. So this is sigma. They're asking me to find cosecant of sigma, right? Where sigma is defined to be this. Good. This is same as that, equals this. Okay, now back to over here. Then in order to, so if this is true, that must mean that I can create a triangle, a right triangle, that has an angle sigma on here, such that this is true, and sigma is related to adjacent over hypotenuse, and then there's this side that's missing. So therefore, 7 squared plus b squared must be equal to 25 squared. Good. So b squared is equal to, wait, what did I do? Okay, equals to 25 squared minus 7 squared. So b squared is equal to 25 squared, so that's 625 minus 49. 25 squared minus 49 gets you to 572. 576, sorry. And then we want the square root of that. So gets you to 24. Plus or minus 24. And now in quadrant 1, this is going to be positive, right? Positive 24. If I was going to think about this in the first quadrant, this is the y, and this extended this way. I can think about it in quadrant 1. In Q1, this would be equal to positive 24. And then, of course, the other place where this could be true is if it was in quadrant 4. If it was down here and came up that way, we'd still have positive 7, positive 25. We'd still have a value where this would be true. But how do we know that we don't go to quadrant 4? Right? I'll put consider or... note that sigma could also be over here, or there could be a triangle over here that's equivalent, it's got the same sigma there, and then we'd end up with another triangle. This one would be 25 on this side, 5 on this side, and this one would be 7, and then you go, okay, well this side's negative 24. Okay, we have another triangle. But this one can't be the one we're working with. Why? Because in order to get to quadrant 4, we got two options for sigma here. Either it's going to be some small negative value, like let's say for a second that this is angle 35 degrees or something. Then that would mean that this would be negative 35 degrees. And what's wrong with that? Well, we've restricted our domain for this thing. It's got to be an angle between 0 and 180 degrees. No negatives. Same thing if we go in the other direction. Like, okay, the other way to get this triangle is to start here and go that way, which we end up with an angle that's bigger than 270 degrees but less than 360 degrees. And again, the problem is that we've restricted our domain. This is why we restrict our domain, so that there is no ambiguity about which triangle we're working with. Good? Questions, 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 questions? Okay, so as long as we are dealing with cosine, we were stuck with triangles that are in quadrant 1 or quadrant 2. That's the only place that we can have a sigma value that satisfies this condition that's between 0 and 180. Good, good, good. Okay, and so now that we have our triangle and we're happy that it's in quadrant 1, now that we can solve this. And remember that this is 1 over sine, and sine was equal to opposite over hypotenuse. So I can tell from my triangle that this, I can tell from my triangle that this is equal to 25 over 24. Any questions? No? No? We're good? We're good? We're good? Good, 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 good. Okay, let's try one more of these, the ones that leave it abstract. How about 36? Sine of tan inverse of x. We want 6.4, number 36. We got sine of tan inverse of x. And it says, write the expressions. The instructions just say, rewrite the expression as an algebraic expression in x. Okay, so once again, I'm going to take this little part in here and again realize that this equals to some angle, right? We input a decimal value and the output is an angle. So we set tan inverse of x equal to some angle theta, right? Because again, tangent of the regular tangent function works this way. We input an angle, right? An angle, and the output is some decimal value, some decimal value. And for the tangent function, there's no restrictions. Some decimal in r, some real number is the output. Okay, so now we get to input some real number into here. Some real number goes into there, and the output is an angle. Now we do restrict the domain of our function in order to make it one-to-one, and the restriction is that it's got to be an output of an angle that's between negative 90 degrees and positive 90 degrees. Right? In other words, it must be in Q1 or Q4. Right? If you go negative 90 degrees, you end up in quadrant 4. Good? Okay, so we set this part equal to some theta value. Let's make this in red. So this is some theta value, and that's what this is. So they're really asking me for sine of theta. Wow, that's unprofessional. 1 second. Hello? Hello? Oh, Yeah, sorry, I'm in a meeting. I can't talk right now. Have a good day. Okay, sorry about that. T-Mobile bugging me. Don't ever sign up with T-Mobile. Don't do it. Anyway, so sine of tangent inverse of x is this. So I'm going to stick that theta in there, right? So they're asking me this. This is what they want to know. What is sine of theta? Okay, now back to this. This is true if and only if it's true. We get away from this tan inverse, right? If and only if it's true that tangent of theta equals to x. Good. Okay, so now we can create a triangle. We have our triangle. Tangent of theta is opposite over adjacent, and since it's just equal to x, then we can put a little 1 underneath it. Let's erase that. And write it as x over 1. That's the same thing as it equals x. Right? So here is theta. It's opposite over adjacent. So it must be true that this missing side satisfies the statement that 1 squared, well, I'll say, let's call it down. Right, so we're missing this side over there. So it must be true that 1 squared plus x squared equals h squared. Good. So h equals to plus or minus the square root of 1 plus x squared. And again, we are ignoring the negative. Ignore the negative. So that's what this is. This can be the square root of 1 plus x squared. So we're ready to answer our question. They want to know what is sine of theta, and here is theta. Sine of theta is opposite over hypotenuse, so my final answer is going to be that this is equal to x over square root of 1 plus x squared. Any questions? No? No? We're good? Good. Okay, so let's move on to the last section we're going to cover in this chapter. Okay, so the last section we're going to cover in this chapter includes the law of sines. Should be a nice, easy section since we're just using the application of the law of sines. We're not really going to derive it, not responsible for its derivation. We just got to use it, apply it, and move on with our lives. The law of sines. The law of sines refers to the following. It's pretty easy, I think. Is this. Think of a triangle, any triangle, where it doesn't have to be a right triangle, so it might look something like this. Oops, that was an ugly. I knew it. So, damn it. think it'd be a little easier to connect things with this. But anyway, okay, so here's some random triangle, not necessarily a right triangle. We'll call that angle A, angle B, and angle C. So we usually like to adopt the idea that the capital letters are angles. So these are the internal angles of a triangle. We know from triangles that it must be true that the sum of all the angles, angle A plus angle B plus angle C, must add up to 180 degrees, right? That's from geometry. The sum of internal angles of a triangle must add up to exactly 180 degrees. And then the side opposite the angle, we usually like to use a lowercase letter. So this would be side A, side B, and then side C, right? Opposite to each other. The law of sines is really easy to state. It simply says that sine of an angle divided by its opposite side is equal to sine of another angle divided by its opposite side, or the last one, sine of the third angle divided by its side, right? That all three of these ratios are equivalent to each other. Good. So this is helpful when we're trying to, so again, we're not proving it, we're just showing that that's what the law of sine says. And we get to use this to solve a triangle when some information is missing. So if we know 3 out of 4 of any of these two statements, say these two right here, if I happen to know, say this one, and this one, then I can solve for this one. Good. Or maybe focusing on these, maybe I know this one, and this one, so I can solve for this one, right? So whenever you know 3 of them, you can find the other one. So you need either 2 sides and 1 angle, or maybe 2 angles and 1 of the sides, right? But what you cannot have is just 3 angles. That's not going to help you figure out the missing value, because you won't be able to set up an equation from that. And what you cannot have is just have 3 sides, side, because then that again doesn't help you set up this. Now you can solve it by another method. You might be able to solve it by another method, but it won't be the law of sines, right? So the law of sines requires you to have at least 3 pieces of information, and they have to mix and match. You have to have at least 1 side, at least 1 angle. Good. Okay. If we have, so here it is, law of sines, sine A over A, sine B over B, sine C over C. Good. All right, let's just jump into an example. A satellite orbiting the Earth passes directly overhead at an observation on Phoenix and Los Angeles, 340 miles apart. At the instant when the satellite is between the 2 stations, its angle of elevation is simultaneously observed to be 60 degrees in Phoenix and 75 degrees in Los Angeles. Okay, so here's a nice little image for it. There's a satellite between the 2 cities. So here's Los Angeles, here's Phoenix. The angle of elevation from Los Angeles is 75 degrees. The angle of elevation from Phoenix is 60 degrees. Good. And we know that they are 340 miles apart. So from that, we can draw this basic triangle that comes up this way, comes across. And we know that this guy is 75 degrees. This guy is 60 degrees. We know from the fact that the sum of all internal sides must add up to 180. We know that that side must be equal to 180 minus 75 minus 60. Good. So what is that? 120, 155? Come on. 180 minus 75 minus 60, 45. Okay. So we get that this must be 45 degrees. We also know that this distance from there to there is 340 miles. From there to there. And they're asking, what's the question? A satellite at the instant. How far is the satellite from Los Angeles? Right, so this is the one that they want to know. How far is the satellite away from Los Angeles at this instant? Okay, so law of sines sets up a relationship between an angle and its opposite side. So I'm going to say that sine of 60 degrees over x is equal to, and now I get to pick one of the other ones. Now if I pick 75 degrees to work with, I don't know its opposite side. So you really can't use that one. But if I use 45 degrees, I already know its opposite side. So I can set up the relationship sine of 45 degrees divided by 340. Good, so I got three things I can solve for. So I can solve for x, and so x, right here. I can solve for x by multiplying both sides of this equation by x. X on this side cancels, times x on that side, and then multiplying both sides by the reciprocal. And so I'll end up with x equals to 340 times sine of 60 degrees divided by sine of 45 degrees. Good. As long as we're working with straightforward triangles, then we know that sine of 60 degrees, right? These are some of our known triangles. Here's 60 degrees, here's 30 degrees, there's 1, root 3, and a 2. So sine of 60 degrees is root 3 over 2. And the other one is the other standard triangle, which is 1, 1, root 2, where this is 45. So we know that sine of 45 degrees is 1 over root 2. So x equals to 340 times root 3 over 2. I'm sorry, 340 miles, which is 300, not 344 degrees, divided by 1 over root 2. And we can just punch that into our calculator and get an answer from there. And let's see, this is probably the same thing the author did. Sine of 60 over b, sine of 45 over 340. Yep, you get the same equation. And then hopefully this whole thing turns into 416. Any questions? Let me make sure that that's what we get. Root 3 divided by 2 times 340 times root 2. Yeah, I get 416.4133. So we just round to 416. Any questions? Any questions? Questions? No? Okay, now when you're solving these, we might run into something we call the ambiguous case. So the ambiguous case is noting that sometimes the information that's provided might result in several, or it might result in two different triangles that satisfy the conditions given. There's also going to be the possibility that we get no solution. So here's some drawings of some examples. So let's say that angle A is given, side B is given, and side A is given. So if the information provided looks like this, obviously this would be a case where there is no triangle. right? So just because they tell you find a triangle that has angle 75 degrees, side 17, and another, side B is 17 and side A is 2. Just because information is provided for you doesn't mean that it actually is a triangle. It might be a case like this. Or it might be a perfect case like this where there is exactly one unique triangle that satisfies the conditions given. Angle A, side B, side A, give you exactly one. Or it might be a case like this one, again, that gives you a unique solution. Or it might be a case like this where there's more than one solution. There's two possible answers to it, right? So here, so remember the angle A is given, side B is given, and side A is given. But maybe the information provided is such that we might have two answers. We might have this triangle out here, the bigger triangle, or we might have this triangle in here. So if you're in this case, where there's more than one, you'd have to provide both of them. And then maybe, depending on the word problem or something, it might be appropriate that one triangle satisfies the word problem more than the other. Or maybe both are solutions. Okay, so here's an example. Solve this triangle, right? And we have angle A is 45 degrees, and we have side B is 7, and side A is 7. Okay, 7 root 2. So we need to set up our sign. The law of sines indicates that sine of 45 degrees divided by its opposite side, 7 root 2, must be equal to, and now we have to use sine of B over 7, right? I couldn't jump to angle C because I don't know anything. I don't know angle C, and I don't know its opposite side, so both of those are blank. I gotta use sine of B and 7 in order to solve this. Okay, solving for B, I'm just going to multiply both sides by 7. Multiply this side by 7, multiply this side by 7. Right, that solves for sine of B. Sine of B equals to this product. Now the 7's cancel. So it's really just going to be sine of 45 degrees divided by root 2. And we know from our standard triangles that sine of 45 degrees is 1 over root 2 divided by root 2. So we can simplify this by multiplying the numerator times the reciprocal of the denominator. Put a little 1 there. And so we end up with sine of B equals to 1 over root 2 times the reciprocal of the denominator, root 2. So the whole thing just equals to 1 over a half. 1 over 2, so it's 1/2. So we have this. Sine of B equals a half. Okay, this is going to be one of our simple triangles. Good. So we know from our standard triangles that if we have this, we have 60 and 30, 1 root 3 and a 2, sine of 30 degrees equals to 1/2. Good. So sine of 30 degrees equals to a half. Good. But remember that sine is equal to positive 1/2, a positive answer in quadrant 1, but also in quadrant 2. Good. Let me draw it up here. Right, I can have a triangle here that has 30 degrees, and then this would be 1 over 2. Or there's another triangle that I can create over here in quadrant 2 that has a 1 and a 2 there. Right, remember here this is positive, and then over here this would be negative. So the x-coordinate is negative, and so that affects like the cosine, but it does not affect sine. Sine is still positive 130. and that would be where this is 30 degrees there. And so that would be the reference angle. There is an angle that goes from here to there that results in a triangle in quadrant 2 that has a reference angle of 30 degrees. That must be 150 degrees. Good. So we can conclude that sine of 150 degrees is going to be equal to sine of 30 degrees, and they both equal 1/2. Is that okay? Good, 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 good. Okay, so from here we get that B must be equal to 150 degrees or 30 degrees. Now going back to our triangle, we can easily eliminate the case of 150 because we know that the sum of the interior angles must be 180, right? So B can't be equal to 150, right? Because 45 plus 150 is already bigger than 180. So B can't possibly be 150 degrees. So we've narrowed it down to 30, right? So that helps us solve this triangle down to this. We're getting a little closer. Now we definitely know that guy has to be 30 degrees. And so now they add up to 75. That means that this thing is 105 degrees. This guy is 180 minus 45 minus 30. So that equals to 105 degrees. And now we can set up another law of sines to find the other missing value. So now we can set up that sine of 45 degrees divided by 7 root 2 is equal to sine of 105 degrees divided by the missing value lowercase c, right? This distance there. Good. Questions? So 105 degrees is obviously in quadrant 2. 105 degrees is there. So it'll create a triangle in quadrant 2. I know that sine of this angle is going to be positive because it's in quadrant 2 and sine is positive in quadrant 2. But this is then going to be 75 degrees. This is 90. So this must be 15 up here. And this is just not one of our standard triangles, right? Remember, by hand, we can only solve triangles involving 30, 60, and 45. And soon we'll be able to do this one because it's just the addition of a 30 and a 45, but we haven't gotten to that yet. So at this point, really, we just have to rely on our calculator. Sine of 105 degrees, get an answer, and we can solve this that way. Okay, so we're going to solve for c, multiply everything by c, and then multiply everything by its reciprocal, and we'll end up with c equals to sine of 105 degrees times 7 root 2 divided by sine of 45 degrees. Put a 1 there. And then we can just reach over to our calculator and find this answer. Here, quit. Sine of, first of all, make sure that you're in the right mode. Mode, I'm in degrees. Okay, quit. Okay, so sine of 105 degrees is equal to that decimal. I'm going to take that decimal and multiply it by 7, multiply it by root 2. I get that for my numerator. And when I take that previous answer and divide it by sine of 45 degrees. So I get that. 13.523. 523. 13.523. Good. All right, so we've solved our triangle. We know that this side must be 13.523. Any questions? No? No? Let's see what the author did. Okay, they set up the same thing. Sine of b equals to a half. And then we note that there are two solutions, either 30 or 150. Right? 150 gets eliminated right away. And that's why we only end up with one possible answer. But there will be cases where you, at this stage, you end up with two different angles, and maybe they both satisfy a triangle. Right? In this case, the 150 was eliminated because it was too big, and it ended up giving summing to 195, larger than 180. But in other cases, you might just end up with two solutions. Okay, and yep, we got the same answer, 13.5. So in general, if sine A is less than 1, we check the angle and its supplement as possibilities, and any smaller, okay. So the case where we might have two solutions. So here's another triangle. We have triangle ABC, where capital A, angle A is 43.1 degrees. The side opposite is 186.2. The side opposite angle B is 248. So here's a case where we might have two possible triangles. Now, when you first run into this, this is the solution already. They just give you this. When you first run into that, you might not know that you have two solutions. So you might just draw it like this. Right, so here is angle A. And opposite side of angle A is 186.2. And then here's angle B. The side opposite angle B is 186.2. And here's C, and then here's C. Good. Okay, so we go about solving this like we always do. So this angle is 43.1. So we set up our sine, law of sines. Sine of 43.1 divided by 186.2 must be equal to sine of angle B divided by 186. Oops, I messed up. B is 48. Side B is 248.6. 248.6. Okay, so sine of B must be equal to 248.6 times sine of 43.1 divided by 186.2. Good, so then we go over to our calculator and figure out what this is. Clear. So sine of 43.1 degrees, enter, times 248.6, enter, divided by 186.2, enter. So we get this, 0.9125. So that's what I'm trying to solve here. When does this give us a true statement? 91.225. Right? So we're trying to find an angle such that sine of that angle equals to this decimal. Good. Now that's not a standard result, so we have to use our calculator to find it. We don't know how to do that without that. So we want to take sine inverse of both sides. Sine inverse of this side, sine of b, equals sine inverse of 0.91225. So these two operations reverse each other. They're inverse operations, so they undo each other, resulting in just b. b is sine inverse of 0.91225. And we just punch that into our calculator. And we get that sine inverse of 0.91225 is approximately 65.82 degrees. .82 degrees. Okay, but this is when we have to start thinking about the other possibilities. When we use sine inverse, remember we restrict the domain of our sine function in order to be able to make the sine function a one-to-one function. But there might be another answer, right? So let's attack it from this perspective. If you recall the general graph of a sine function, and we'll spend more time on this in the next section when we go back to chapter 5. But remember, the general shape of a sine function goes like this. Right? This is sine of theta. This goes up to there. As we plug in different angles, we get different outputs, and this goes up to a maximum of +1, and this goes down to a minimum of -1. Right? And then this comes back down this way and goes this way down there and goes back up that way like that. Okay, so 65 degrees is going to be somewhere around here. So here is 0.91225 is right here. And it connects to this value, connects to this value right here, that's about 65.82 degrees. Okay, so that's this point. But if we got this point because we went backwards, right? We asked our calculator, what's the angle such that sine of that angle equals to 0.91225? But from the picture, I can see that there's in fact another one over here. Here's another answer. There is another angle over here. There's another angle right there, such that sine of this angle is also going to be 0.9225. And in fact, if this pattern continues, right, this goes on forever in the same oscillating up and down, I can see that eventually there's going to be another one over there and another one over there, and this pattern goes back in this direction. So I know that eventually there's going to be another one over here and another one over there. There's really an infinite number of angles such that sine of that angle equals to 0.99125. So what do we do in math? We restrict the domain. Whenever we work with our calculator and we ask it to give us a sine inverse function, it only works in this little range. It restricts the domain to be somewhere between -90 degrees and +90 degrees. Good. So if your answer was actually something to the left of -90 degrees, you're going to have to do some math to figure out the other solutions. Or if you want an answer that's to the right of +90 degrees, then you're going to have to do some work. Okay, so from my picture, I can see that it's going to be in quadrant 2, right? Because here's 90 degrees, the sine function crosses the horizontal axes again at 180 degrees. So somewhere between 90 and 180 is this other value that I can see from my picture is going to solve things. Also, we know that quadrant 1 and quadrant 2 are the places where a sine function gives you a positive output, right? I'm looking for the places where sine of the angle equals to this result, which means it's positive. Good. So there could be some triangle here that has 0.91225. over 1. Here is one triangle, opposite of hypotenuse. Here is one possible value. That's going to give you sine of b equals to this over that. And so we get this, right? And then the other place where it could happen is that maybe it's in quadrant 2. Maybe the triangle goes back this way, where maybe this side is 0.91225 and the hypotenuse is 1, and then of course we'd have a negative x value there, and here we'd have a positive x. Here cosine would be positive, and here cosine would be negative. So if they gave me additional information and they told me that not only is this true, but also cosine of this b is negative, oh, okay, then I know we're in quadrant 2. Okay? Good? Good? Okay, so now that we know that, according to my calculator, this guy is 65.82 degrees, then this guy must be something such that its reference angle is equal to 65.82 degrees. So it must be 180 minus 65.82 degrees. Questions about that? Good, so that's 180 minus 65.82 gets you to 114.18, or 114.18 degrees is the other possibility, or 114.82 degrees. Any questions about that? Questions. And then of course that means that this is 65.82 degrees is the reference angle of this triangle in quadrant 2. This one is quadrant 1, and this one's in quadrant 2. Any questions at all? Questions? Okay, so then we have to work under both possibilities. It's possible that one option is that the angle is 65.82 degrees, and that results in this larger triangle. So one option, one possibility, is that this angle right out here is 65.82 degrees. That's one possibility, and that gives you this big triangle. And then, you proceed forward from that. You have this big triangle that looks like this, and from that we have 65.82 degrees. And then over here we have 43.1 degrees. So then we can say that this guy up here must be 180 degrees minus 43.1 minus 65.82. So 180 minus 65.82 minus 43.1. So it's 71.08. So this guy is 71.08. And we've also established that this side is 248.6 and this side is 186.2. And now we can use, again, another law of sines to find the missing side. Any questions about that? Okay, but there's another one. And so the other one could be that, in fact, no, it's not 65.82. Maybe it's this possibility over here. Maybe it's this one. maybe this is the case where really the answer that was that this is 114.82. So maybe the triangle doesn't look like this. Maybe the triangle is more like this. Right, where this side is 114.82 degrees, and this side is 43.1 degrees. And so now this side is 180 minus 43.1 minus 114.82. So 180 minus 114.82 minus 43.1 gets you to 22.08. 22.08 degrees could be that guy. Good. And then we already knew this side was 248.6, and this side is 186.2. Okay, so we can either end up with this triangle right in there or the big triangle. They're both solutions to this given the information provided. Questions, 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 questions? So, yep, 65.8, 114.2, they're both possible angles. And from there, you can set up another law of sines statement to solve the missing value. So in one case, you're going to end up with the missing value being equal to 257.8. And in the other case, you're going to end up with the missing side being 105.2. Now, if this was a word problem, maybe one of them makes sense and the other one doesn't. Maybe you know for a fact that the answer has to be bigger than 200 given the constraints of the word problem, so maybe you can eliminate this one. Or the other way around, maybe you know that the given answer has to be less than 150, so you know this one is it. Or maybe you get to choose. Maybe the whole point is to choose the easiest answer or the one that fits most. So maybe you have a choice. Good. So here are the two completed triangles. Any questions? No, 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 no. Okay, sometimes you got to be careful. They give you information and you move forward thinking everything's fine and you set up your triangle, and it might be a case that has no solution. So in this case, solve triangle ABC where angle A is 42 degrees, side A is 70, side B is 122. So you move forward in good faith. You have no idea that there's something wrong here. So angle A is 42 degrees, opposite side is 70, angle B is unknown, side B is 122. Okay, so then we set up our sine function, sine of B over 122 equals to sine of 42 over 70. Okay, so you move forward, sine of B equals to 122 times sine of 42 degrees over 70. Okay, if something turns out to be wrong, and this is a no solution triangle, one of a couple of things is going to happen. When you do this, you're either going to get sine of B equals some number that's outside of the range of sine. Remember, sine should give you an output that's a decimal between -1 and 1, or including -1 and 1. So you can't have it be equal to positive 1.3, for example. Or you can't have sine of theta equal to -1.42, right? So that might be one of the clues that something is wrong, that this thing equals something like that. Or if you proceed, then again, you might have, so you solve for B, and then you set up another law of sines to solve for the other angle. And the other thing that might happen is that you end up with 3 internal triangles that do not add up to 180. That's the other thing to look out for. So let's see what your author did for this one. So we set it up in the same way, 122, 70, 42, okay. And then, yeah, so see in this case, we end up with this product equaling 1.17, right? So here we end up with sine of b equaling to 1.17. And so that's how we know that there's no solution. Right? The output to a sine function has to be a value between -1 and 1, inclusive of the -1 and the +1. Good? Any questions about this? No? Good, 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 good. Okay, I think we kind of covered lots of different cases here. And I think they're pretty straightforward for the most part. I think the trickiest thing is finding the possibility of more than one solutions to the inverse function. So you have to keep in mind the restriction on the sine function and the restriction on the cosine function and the restriction on the tangent function, so that you can potentially find another angle that also satisfies the conditions. Any questions? No, 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 no. All right, let's take a little 10-minute break and we'll come back. We'll get started on chapter 5. Again, another introduction to trigonometry. So hopefully also pretty easy. All right, so both chapters 5 and 6 were introductory chapters to trigonometry from different perspectives. So we skipped 5, we did 6, and introduced trigonometry. So now we're going to go back and reintroduce it from a new perspective. But keep in mind that this is an introduction. This is supposed to be something that can be presented to someone that doesn't know anything about trigonometry. So it's tempting to jump in and come with knowledge of sines and cosines, as we already have a lot of knowledge. But remember that, the point of this is to introduce the subject. So you're not supposed to know what sine of 30 degrees is or anything like that. They're introducing it to you. Okay? All right, so this introduction to trigonometry begins from the perspective of the unit circle. Now, remember that the formula for any circle is this. Remember that we had x plus, minus h. X minus h squared plus y minus k squared equals to r squared is the general formula for any circle. General formula for any circle with radius r centered at point h comma k. Right, so if we saw x minus 3 squared plus y minus, let's say plus 2 squared equals to 9. Okay, so this would be 3 squared. So it's got a radius of 3, and it's centered at 3 comma, and then this would be y minus -2 squared. So the center is at 3 comma -2. Good. Questions, 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 questions? We can confirm that real quick here with some Desmos. So parentheses x minus 3 close parentheses to the power of 2 plus y plus 2 close parentheses, to the power of 2 equals 9 is this circle. Good. Where the center is going to be right here. Anyway, the center is here, which is 1, 2, 3 units. So x equals to 3, and then y equals to -2. So 3 comma -2 is the center of the circle, and the radius is 3 units. Good. If I instead change it from -3 to -4, it's going to keep the same radius and just shift the circle to the right by 1 more unit, or by 5, shifts it even more. If I change it from -2 to, +2 to -2, then it shifts it up instead. Right, so the value here controls the x-coordinate of the center of the circle, and the coordinate there determines the y-coordinate of the center of the circle. Right, so we can leave these as little sliders now. Say this one is this one, and this one is B, like that. And so now, as A changes, it changes the center of the circle left and right. And as B changes, it changes the center of the circle up and down. And then the radius will change if we change the r value here to different results. So we can come back here and change this to r squared and make r another slider. And then as r gets bigger, then the radius grows. And so we can again move this around. Okay, so that's circles. But in particular, the unit circle is when the radius equals 1. Right, so now going back to this thing, the unit circle has the formula x squared plus y squared equals to 1. Right, so this is a circle centered at the origin, 0, 0, with radius 1. Good. Circle centered at 0, 0, the origin of our Cartesian coordinate system, with radius 1. Questions? Okay, we're going to be working with the unit circle, and then we're going to define some new language for this section. Terminal points and reference points, and then we're going to use that information to again introduce the topic of trigonometry from a different perspective. Okay, so here is our standard unit circle centered at 0, and here's the equation for it. Remember that this means this shape, this circle, is an infinite number of dots, such that the ordered pairs that identify those dots, the ordered pairs, satisfy this equation. Good. Okay, so the equation is x squared plus y squared equals 1. Here we have a unit circle. So for example, show that this is a point on the unit circle. In order to show that this is a point on the unit circle, it must satisfy the equation. Right? Any point on the unit circle satisfies the statement x squared plus y squared equals to 1. Right? Blank squared plus blank squared equals 1, where the first blank is this x value, it's the one that goes there, and this one is the one that goes there. Right, so if it's true that this is a point on the unit circle, it must be true, right? So for us, it must be true that when we have blank squared plus blank squared, it must be equal to 1. This point is going to be on the circle if it's true that when I do this, the x coordinate goes there, the y coordinate goes there, then we get a true statement. Root 3 over 2 and root 6 over 3. oops, sorry, this is over 3. Root 3 over 3 and root 6 over 3. Okay? So now we simplify and verify that it's true. So we end up with positive 3 over 9 plus positive 6 over 9 equals 1. And then, luckily, they already have the same denominator. So this just equals to 3 plus 6 over 9 equals 1. So 9 over 9 equals 1. And yep, that's true. So we've confirmed that this is definitely an ordered pair that satisfies this condition. Therefore, it is a point on the unit circle. Is that clear? Any questions about that? Okay, so showing that that guy was on the unit circle is pretty easy. We're going to define something called terminal points on the unit circle. And we're going to define them with this t value, lowercase t. So suppose t is a real number, a positive number. So for our purposes, t is only ever a positive number. So what we're going to do is think of t as a distance around the circumference of the unit circle. Right? So if it says 3, then we're going to go 3 units. If it says 1.5, we're going to go 1.5 units on the unit circle. Good? And then wherever t ends, starting here, we're going to start at the point 1, 0 and measure our way out. And then wherever it ends, that point will be the point that is referenced by that t value. Good? And that's what we call the reference point. Questions, 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 questions? Good. So if t is a positive distance, we go this way. If we have a minus t, then we're going to go in the opposite direction. Good, 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 good. Okay, so terminal points on the unit circle. So in this way, we arrive at the point x comma y on the unit circle, which we call the terminal point of our value t, of our reference number t. Good. Questions, questions, questions? Remember that the circumference of the unit circle is just going to be 2 pi, since the circumference of any circle is 2 pi r. And in this case, since it's a unit circle, r equals to 1, therefore it's just 2 pi. Right? So the distance all the way around is 2 pi. And so if we're looking for the terminal point determined by t equals to 2 pi, then that's going to land in 1, 2. I'm sorry, 1, 0. Good. Questions, questions, questions? This is all sounding very familiar. We were working with something very similar in Chapter 6 involving angles and radians. But here, remember, we're introducing the same sort of logic. We're just using different terminology. So here's some standard ones. Let's zoom in a little bit. So here's some standard ones. If the t value is pi over 2, then we know we go exactly 1/4 of the way through our circle, right? And this is just knowing that the whole thing is 2 pi. Therefore, half of it is pi. The whole thing is 2 pi. And so we know some standard ones. Good? Questions, questions? So obviously, this must be the point 0, 1. This must be the point -1, 0. This must be the point 0, -1. And this one must do a full lap all the way around and get you back to 1, 0. Any questions on these standard ones? So as long as t is given in terms of some nice multiples of pi, then we can figure out those standard values. Good. And we can figure out maybe one more in a somewhat easy way. We'll get to that one. But then we can also find a few others just based on these. So on these straightforward ones. So if we wanted to figure out the terminal point associated with t equals to 3 pi, right? So remember that 2 pi is one complete rotation, and then you go another pi, so you end up at point -1, 0. right? That's what this one's going to be. One complete rotation all the way around, and then an extra part. Right, so man, I can't draw circles. Okay, let's say that that's the unit circle. So if that's the unit circle and you're going to be traveling along the unit circle, you're going to do from there to there is pi. Traveling all the way to there, that's 2 pi. And then you're going to keep going until you end up there. Right? So we end up with the point -1, 0. Good? Okay, for this one, we're traveling in the negative direction, so we're going to travel clockwise, always starting at the point 1, 0. So now if we travel minus pi, we go in this direction, and we end up in the same spot, -1, 0. Good. So both of these t values give us the same terminal point. Good. And then -pi/2 is going to go, again, clockwise. Starting there, and we'll go clockwise this way, because it's -pi/2, and we'll end up at this point, which will be the point 0, -1. Any questions? No? No? 5.1 should be really easy. I know it's tempting to think that maybe you're doing something wrong because the questions are so easy, but they really are that easy. Okay, so here's what the author did. So same thing, we have the unit circle. We start here, we travel one full lap, and then an extra pi, which gets you to -1, 0. For part B, we start here and we go minus, so we go in this direction, minus pi. We end up at the point -1, 0. And then for the third one, we go in this direction again by -pi/2, and we end up at 0, -1 again. Easy stuff. Good. Okay, well, there's another one that we can figure out, which is this one. Right? And this is another standard one that we can kind of figure out by using geometry. So let's say that we have this unit circle. Let's figure it out. Is this going to give me? No. Let's say that I want to figure out what this is. I have the unit circle, right? So this is x² plus y² equals to 1. It's the unit circle. And then this goes this way, and this goes that way. So this is x, this is y. And then I have another function that goes this way and goes across this way. And this is the line y equals to x, right? So every point on this line is a point where the left side, the input equals the output, right? That's what this is. So points on this line are like the point 3, 3. X is 3, the output is 3. Or the point, over here, 9, 9. Or the point 2.7, 2.7, right? That's what this is saying. So a point on here, let's call it A and B. Well, actually, it's got to be the same. Right? In order for it to be on this line, it must be true that it's A and A. Is that okay? Okay, well, if it's on the unit circle as well, it must also be true that it satisfies this. So I'm looking for an ordered pair such that it's on the line and also it satisfies this condition. So it must be true that a² plus a² equals to 1, right? If we have a, a, this satisfies y equals to x, where both the y is an a and the x is an a. So it satisfies that condition. And it must also satisfy that x squared plus y squared equals to 1, where both the x and the y are both the same value. Good. So then from here we get that this must be 2a squared is equals to 1, which means that a squared equals to 1/2, which means that a equals to plus or minus root 1/2. I'm in quadrant 1, so I know that a must be a positive number, right? So I can ignore that negative and say that a equals to square root of 1/2. Ignore that. And so we can say that a equals the square root of 1/2, positive 1/2. And if we simplify that, we get square root of 1 over square root of 2, which means a equals to 1 over root 2. And then we can rationalize that and say that it's root 2 over 2. Doesn't matter. Okay, and then a equals to 1 over root 2, so that means that both of these coordinates are 1 over root 2. Right, so this is the same thing as root 2 over 2 after we rationalize it. Right, multiply the numerator and denominator by root 2 over 2. And that's how we get to this point right here. When t equals to pi over 4, that must mean that this side is also pi over 4. We know that because this whole thing is pi over 2. Is that clear? This distance, the whole distance, is equal to pi over 2. And if we chop that in half, exactly half, we get pi over 4. That's how we know that this point must be exactly halfway between the two. This is pi over 4, and so is this. This distance from here to there must be pi over 4 as well. So it's exactly halfway. It cuts it exactly halfway. That's why we know that the answer, whatever this ordered pair is, must be on this line, y equals to x. And that's how we're able to solve for that point. And so we get that this point right here, it's the point a comma a, but more specifically, it's the point root 2 over 2 comma root 2 over 2. It's a, which is the point that's right there. Any questions about that? No? Maybe? Sort of? Kind of? Sort of? Maybe? Kind of? Okay, remember, it's tempting to come in and say something about sines and cosines and all that, but we don't have that yet. We're introducing it. So my only statement right here is an algebraic geometric argument that you can present to someone that has never seen trigonometry, has no idea what trigonometry is, and convince them, hopefully, that you know the coordinates of that ordered pair based on the information provided. You have a unit circle. On the unit circle, this distance is pi over 4. This distance must be pi over 4. It must be true that that ordered pair has to bisect this circle, cut it like that in half, and it must be true that the place where it crosses has an ordered pair where the left and the right of this ordered pair, the x-coordinate and the y-coordinate, are both identical. If it's on the unit circle, it must also satisfy this equation, so we can find the value of a that way. Any questions at all so far? Okay, so we have one more valuable point that we've established on the unit circle that connects to a t-value of pi over 4. But what about one of the other common t-values? What if t-value, we have t equals to pi over 6, for example? Well, now we have a lot more trouble, which is why I don't really like to introduce trigonometry from this perspective, because it gets really hard. So now we have a case like this, where t is some value over here, say it's this one, and this guy is pi over 6. Okay, so then there's an ordered pair right here, some value, I don't know, let's call it A and B. Here's A, here's B. Before I did A and A, because I was convinced that the x coordinate and the y coordinate had to be equal to each other, but we don't know that anymore, right? Because this doesn't go exactly halfway. If that is pi over 6, then the rest of it is going to be pi over 3. Goes from there to there. Right? I know that because I know that from here to there is pi over 2. So pi over 2 minus pi over 6 gets you common denominator, multiply numerator and denominator by 3. You get 3 over 6 minus pi over 6. 3 pi over 6 minus pi over 6, which gets you to 2 pi over 6, which reduces to pi over 3. Good? Okay, so it's hard to figure out what this ordered pair is. It'll take a lot of algebra and figuring out what that point is. And in fact, the book doesn't even get into it and just says, it can be solved. You know, it's just this rabbit hole of geometry and angles, and it just gets ugly. So they kind of give up, and they just give it to you and go, okay, well, just trust me. We can use geometry and algebra to figure out what that is. Okay, and then they just give it to you, which is kind of ugly, but all right. So here is what we solved before. We found that one, and then all of a sudden the book just presents this table and says, here are some other ones. This one, the one that's pi over 4, this is the one that we really solved, and we got a nice answer for it, and we can convince anybody with a little bit of algebra and geometry background that this is the right answer. But these are, well, this one and this one are a little bit more complicated, and there was no real justification presented for you in the book. Just a statement that says we can use geometry and algebra in similar ways to find this one and this one. Okay, so for this section, you're going to have to just be convinced. Assume that they can be found using geometry and algebra. Okay? All right, they're on the unit circle, so these ordered pairs also satisfy, remember that in order to be on the unit circle, it must satisfy that the x-coordinate squared plus the y-coordinate squared must be equal to 1. So you can at least double check that these are true. Good, 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 good. Okay, so once we have these, once we assume these are true and they're all in quadrant 1, we can use these to figure out other standard ones, other standard values that are really just going to reference these. So for example, what if t was equal to negative pi over 4? If it's negative pi over 4, well then the negative pi over 4 is going to extend out here into quadrant 4. And then that distance, kind of keeping track of the distance here, is symmetric to the distance there, and positive pi over 4. So it'll have something to do with this. And we just keep track of the fact that the x-coordinate is positive, the y-coordinate is negative. So from that, we can deduce that, let's put it in green, somewhere over here we'll have the terminal point determined by t equal to negative pi over 4 is equal to positive root 2 over 2 comma negative root 2 over 2. Good. Questions, 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 questions? No? No? Okay, so we go down by negative pi over 4. We, because these two are the same lengths away from the point 1 comma 0, we say that their results are related to each other. We just pay attention to the fact that the x-coordinate must be the same as that x-coordinate, and the y-coordinate is negative root 2 over 2. And we'll arrive at another point that also satisfies x squared plus y squared equals to 1. Good, 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 good. Okay, the other one, 3 pi over 4. Figure out this one. Well, that's going to be in quadrant 2. So it's the way I think of it when I see 3 pi over 4. I think of it as 3/4 of a pi, or 0.75 pi. And remember that from here to here is half a pi, 0.5 pies. From here all the way out to here is 1 pi. So 0.75 pies is going to be somewhere in the middle. It's going to be somewhere in quadrant 2. If this was 1.1 pi, then I'd know it's a little bit bigger than pi. It would be over in quadrant 3. And if it was bigger than 1.5 pies, it would be over here in quadrant 4. If it was bigger than 2 pies, then it would do one complete lap, and then I would subtract a multiple of 2 pi to get a, well, we're going to get into those values soon, but it's the same as before. Okay. All right. Okay, so I know that this is going to be some distance over in quadrant 2. So let's draw the circle. Here's the unit circle. And this t value traveled maybe from there to there. So if this is 0.75 pi, then the remainder here must be equal to the remainder here must be equal to 0.25 pi, or pi over 4. So this distance there must be pi over 4. Good. Okay, and so again, we reference that table over in quadrant 1 and deduce that it must have something to do with these values. So it's got to be something to do with positive pi over 4 in quadrant 1, except now we're going to be in quadrant 2. So I know that the x-coordinate must be negative root 2 over 2, comma positive root 2 over 2. Any questions? No? No? Still pretty easy stuff, right? So if we travel from there to there, we'll get to this point there. And we want to say that this distance right there is equivalent to this distance right there. It's just a geometric argument again. And so that's how we can conclude that this point must be related to that point, and then just adjust the signs for it, just keeping track of the fact that it's in quadrant 2. Questions, 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 questions? No? The last one is negative 5 pi over 6. If I convert it into a decimal, 5 over 6 is less than 1, a little less than 1, but I'm traveling in the clockwise direction. So I know it's going to travel this way past half a pi, but not quite over 1 pi. So I'm going to end up over here in the quadrant 3. Here's my unit circle. So this guy is going to travel this way over here, This is half a pi, and I keep going, I keep going, I keep going until I end up somewhere over here in quadrant 3. So this is negative 5 pi over 6. And now I need to figure out the rest of this so I can complete it. And of course, this whole distance would have been pi. So if I find the difference between the two, I'll get this result. And that's just going to be pi over 6. Is that distance right there? Any questions, any questions, any questions? The signs. Okay, well, if I'm traveling in this direction, obviously it's negative. I'm traveling in this direction, it's positive. So I'm just pointing out that this distance is pi over 6. And then, of course, if I take the exact same direction, same distance, but I go in the opposite direction, like this, well, this would be negative pi over 6. So negative pi over 6 plus negative 5 pi over 6, negative 5 pi over 6 plus negative pi over 6 will add up to negative 6 pi over 6, which gives you negative pi. Good? Okay, and so we're saying that this is related to quadrant 1 distance. Go over here, and we look at a quadrant 1 distance of pi over 6. What are the ordered pairs there? And then again in chapter 5 section 1 they just expect you to look at the table to find these results. So this is root 3 over 2 comma 1/2. Root 3 over 2 comma 1/2 is that point. Good, so armed with that knowledge we can go, okay, well now that we know that, then this point over here, the one we're interested in, must be somehow related to that, except the x-coordinate is going to be negative and the y-coordinate is going to be negative. So it's going to be negative root 3 over 2 comma negative 1/2. Any questions? No? 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 Pretty easy. So we go in this direction, and then that's related to pi over 6, which is this one. So that's how we can make our conclusion that this point there must be negative root 3 over 2 comma negative 1/2. Good? Questions, 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 questions? Okay, so we define the reference number to be the reference number t bar associated with t is the shortest distance along the unit circle between the terminal point determined by t and the x-axis. Right, so it's very similar to the idea of the reference angle. Reference angle was equal to the angle between the terminal side of the given angle and the x-axis, whereas this is the distance. T is defined to be the distance around the unit circle, so it's the rest of the distance along the unit circle between the terminal point and the x-axis. So we have some great examples right here. So in quadrant 1, the t value and its reference number are going to be the same. So remember that you want the shortest distance between the terminal point and the x-axis. So it's not this distance to the y-axis. That's not what we're looking for. We want the distance from the terminal point to the x-axis. So we either have this one or we have this one. And obviously this one's shorter. So in quadrant 1, t equals to t bar. Okay. Now once you get over into quadrant 2, if this is t, then the shortest distance back to the x-axis is going to be this little gap here. And so that little gap there is going to be t bar. Good. When you're in quadrant 3, if this is the terminal point, the shortest distance back to the x-axis along the unit circle is going to be to trace back and go this way and get back to the x-axis. If, on the other hand, the angle goes all the way into quadrant 4, then the shortest distance back to the x-axis is going to be this little gap here, which is t bar, right? All looking very, very familiar, right? Very closely related and associated with what we did in chapter 6 involving angles. Good. So how do we find those t-bar values? Well, we have to keep in mind that the distance, the circumference all the way around the unit circle is 2 pi, right? And then halfway along the unit circle is pi. So we can find this one by doing pi minus t bar. We can do this one. We can find this one by saying that it's t minus pi. And this one is going to be 2 pi minus t equals to t bar. We'll see that written down in a second. Good. If the terminal point lies in quadrant 1 or 4, where x is positive, we find t by moving along the circle in the positive x-axis. If it lies in quadrants 2 or 3, where x is negative, we find t by moving along the circle in the negative x-axis, to the negative x-axis. Okay, so find the reference number for each of these values. Okay, so t equals to 5 pi over 6. We already did this one, or something similar to this one, or I guess ours was negative 5 pi over 6. Okay, so for that one we have 5 pi over 6 leads into quadrant 2. So the rest of this little gap here is going to be the reference value t bar, and we find it by subtracting pi minus this number. Right, so this answer, let's zoom in a little more. This answer, the reference number, is going to be the result of taking pi minus 5 pi over 6. Good, that's going to result in pi over 6. 7 pi over 4, right? If this was 8 pi over 4, it would have just been 2 pi, one complete rotation. So it's a little less than one complete rotation. Or you can turn it into a decimal and say that's 1.75, which is definitely in quadrant 4. So we travel all the way around like this to get to quadrant 4. And so the little gap right there is going to be our reference angle. And remember, one full rotation is 2 pi, so that little gap right there is going to be 2 pi minus 7 pi over 4. And when we simplify that, that's how we'll get pi over 4. Good. Negative 2 pi over 3. Again, this is 2/3 pi, which is 0.67 pi. So it's bigger than half a pi. It's less than one complete pi. Right? This is negative 0.67 pi. Bigger than a half, but less than one whole, and you're going in the clockwise direction. So you're going to go in this direction, past the half a pi into the third quadrant territory. And so the reference angle is going to be this one, the shortest distance back to the x-axis. And so we get that by pointing out that this is the same thing as pi minus 2 pi over 3. Right? If this is negative 0.67 pi, then the reference is going to be positive 0.33 pi. And that's how we get this as our answer. Good. Questions, questions, questions? Okay. Now, often almost said radians. Often we see these distances in multiples of pi. Same with radians, we see it in multiples of pi, but it doesn't have to be. So it could just be a number, 5.80. And remember that one full lap all the way around is 2 pi, where pi is approximately 3.14. So one full lap is approximately 6.28. So 5.80 is almost one complete lap, not quite there. And so there's a little gap that's missing. And so this value will be the value 6.28 minus 5.80, which gives you 0.48. Any questions on all that? No? No? Okay, so here's the same.
Yeah.
Oh, yeah, go ahead.
Would be like how many decimal places, just like as a general thumb?
Oh,
Would you
2 is very popular in math. 2 decimal places is usually a good fallback, except in chapter 4 when we're dealing with logarithms and exponential numbers. Then 4 becomes the more go-to standard. There should be information given anywhere, but it's rare that anybody ever asks you for more than 4 decimal places. So I would say if there's no indication anywhere, you can't go wrong with 4 decimal places. I mean, no one's going to fault you for being too accurate, but someone might get mad at you for being too inaccurate. So why not go 4 decimal places? Unless it says, hey, round to 1 decimal place or something, then follow the instructions. But also, keep in mind that lots of things might say, find the exact answer, right? Which that's code for don't round anything at all. So, this one, for example, you would leave it as a reduced fraction rather than convert it to a decimal and approximate it. So keep an eye out for that language as well. It might say find the exact answer. Okay, good. Any other questions? Okay, so it gets a little tricky when you want to find the reference value. Sometimes the answer is to do pi minus the given answer. Sometimes it is to do 2 pi minus the given angle. Sometimes it's going to be to flip it around and say the given angle minus pi. I'm sorry, what? Was there a question? No? Okay, so sometimes it's going to be to take the given angle and subtract pi away from it. Sometimes it's going to be to take 2 pi minus the given angle. So you have to pay attention to what quadrant you're in. That's what will guide your decision of whether to add or subtract pi, or to take 2 pi minus the angle, or if it just equals to the angle given. Right? So you have to figure out what quadrant you're in, and then figure out how to get that little gap, that extra little bit to get back to the x-axis along the curvature. Okay, so some guidelines. To find the terminal point P determined by any value t, use the following steps. Find the reference number t bar, then find the terminal point determined by t bar, and then determine whether it's plus or minus depending on the quadrant that you're in for each of the x or y coordinates. Find the terminal point determined by each of the given ones. Okay, so we've worked with this one already. We already know that it's almost 1 complete pi. It's rotating in the positive direction. So we know that the gap is going to be equal to t bar is equal to pi minus 5 pi over 6, right? Because this is going to be in quadrant 2. And so the reference value is just going to be equal to pi over 6. Good. And in chapter 5, section 1, the way we move forward to find the point is to go back and look at that table, right? The table that was given to you a little mysteriously without really too much justification for it. Where'd it go? This table. Right? So we justified this one. This one we convinced ourselves that it's true. The others, they didn't really convince us, but they told us to trust them. Trust me, there's algebra that can help us figure out what this is. Anyway, so in quadrant 1, pi over 6 is root 3 over 2 comma 1/2. Okay, so from table, we have this thing like this, and this is root 3 over 2 comma 1/2. Good. Okay, but now we know we're in quadrant 2. So if I did a circle and I went like that and I went like that, I know that this t value would go past there and somewhere over here, and I would end up with a point over there. And I know that the x-coordinate would be negative and the y-coordinate would be positive. And from my table values, referencing the table section 1, quadrant 1, this would be negative root 3 over 2, comma, positive 1/2. Good. Any questions? Good. Okay, what about the others? Well, same sort of thing. We find the terminal value. Now, we've already found these ones, right? 7 pi over 4 is somewhere. Didn't we find? Here it is. 7 pi over 4. 7 pi over 4 is b. So we saw from before that this must be the answer, pi over 4, for the reference angle. And negative 2 pi over 3, we saw that the reference angle is pi over 3. So this is for part A. For part B, we know that to get the reference value t hat, this is going to be equal to 2 pi minus 7 pi over 4, which is going to lead to pi over 4. And from the table, we know that this should be root 2 over 2 comma root 2 over 2 in quadrant 1. Now we just have to point out that the given value is in quadrant 4. So if we draw this circle, then 7 pi over 4 is going to travel past pi, past 1.5 pi's, all the way out to somewhere over there. Right, this is 7 pi over 4. And this is the point we want, right there. And it's going to be related to this one, except the x-coordinate is positive, the y-coordinate is going to be negative. So this is going to be positive root 2 over 2, comma, negative root 2 over 2. That's our answer to part B. Any questions? So it's kind of silly, I think, that the answer comes from just looking it up on a table and determining what quadrant you're in. Okay, part C. All right, so now this time, T bar, we know that this is going to end up in quadrant 3, right? This is a little less than 1 pi, and it's going in the clockwise direction. So I know that T bar is going to be found by doing pi minus 2 pi over 3, which is going to result in pi over 3. Good. Okay, and so from the table, we're going to get that this is 1/2 comma root 3 over 2. Good. And so we just have to determine where it is on my unit circle. So if I have a unit circle like this, coming down this way, coming down that way, this is going to be negative, so it goes in this direction, negative 2 pi over 3 goes out to some point there, negative 2 pi over 3. And now this is the point we're interested in. And so it's going to be the case that the x-coordinate is negative, the y-coordinate is negative, so it should be negative 1/2 comma negative root 3 over 2 is the point we're interested in. Any questions? Any questions? Okay, let's see what the author did real quick. Oh, look, I kept scrolling way up, and here's the table. So there's the table given. Reference value of pi over 6 is right here. So we have this one. These are all in quadrant 1. So all we have to do is adjust our answer to make sure that we point out the terminal point in the appropriate quadrant. Good. So this is going to be in quadrant 2. And then from the table we can figure out the same results we needed for the other ones. Okay. Any questions at all? Okay, once we go past a value of t that's bigger than 2 pi, that means that we've done more than one complete lap around, right? So that we can figure out where it's going to terminate on the unit circle by removing multiples of 2 pi. We can also go in the other direction and subtract 2 pi from a value and get to another point on the unit circle that gives you the same terminal point. Right? So in general, we can add or subtract multiples of 2 pi to any number without changing the terminal point. Good. So find terminal points determined by this. Okay, so it's 29 over 6. We can turn that into a decimal. That's going to be 4. So this is the same thing as t equals 2. And then as a mixed number, it goes into it 4 whole times. That gets me to 24. And then 5/6 as a mixed number, pi. (29 divided by 6 gets you to 4.8. T equals to 4.83 pi, right? But remember that 2 pi is 1 lap, 1 full rotation, and 4 pi is 2 complete rotations, and this is more than that. So we can subtract 2 pi away from this and still end up at t equals to 0.83 pi. Well, that looks confusing. We can take away 2 pi's from this and end up with another t value that ends up in the same terminal point. Good. So let's figure out what this is in terms of an exact answer. So if we take t equal to 29 pi over 6 and subtract 4 pi, then t equals to 29 pi over 6 minus, and if we multiply this by 6 over 6, get a common denominator, we get 24 pi over 6, which then gives us 5 pi over 6. Good. So t equals to 29 pi over 6 is the same thing as saying t equals to 5 pi over 6 plus 4 pi. So 5 pi over 6 will be a t value that determines a terminal point which is the same terminal point that will be determined by 29 pi over 6. Any questions about that? Good. And what is that terminal point going to be? Well, 5 pi over 6 is in quadrant 2. We need more space here. Uh, 5 pi over 6 is in quadrant 2. There's our unit circle. So from here all the way out to, say, around here, this is 5 pi over 6, which means that this little extra piece right there is going to be determined, that's going to be the reference value. So it's going to be determined by pi minus this. So T bar equals to pi minus 5 pi over 6, which is going to be equal to pi over 6. Good. So from our table, and we go over to our table, from table, we'd go look it up. The table is somewhere around here. And we get that pi over 6 is root 3 over 2 comma 1/2. Root 3 over 2 comma 1/2 in quadrant 1. But here we're in quadrant 2, so from there I can conclude that this must have an x-coordinate that's negative, negative root 3 over 2, and a y-coordinate that's positive, so positive 1/2. Good, so we've established that t value of 29 pi over 6 or t value of 5 pi over 6 both result in terminal point negative root 3 over 2 comma positive 1/2. Right, once you go here, 5 pi over 6, if you do one complete lap, another complete lap, then you end up doing 29 pi over 6, and you'll end up in the exact same point. Questions, questions, questions? So here in red is 29 pi over 4, one complete lap, another complete lap, two complete laps, and then finally we end up there. In red, it is 29 pi over 6. And if we just do 5 pi over 6, we go from here to there and stop. Either way, they both determine the same terminal point. Right? Remember, we get this by finding the reference value and then looking it up in the table in reference to quadrant 1. Any questions? I think chapter 5, section 1 is really easy, but it's confusing because I think you already have a lot of knowledge of what trigonometry is, and I think there's this desire to insert your knowledge of trigonometry into this, since it all looks really familiar, right? We know what root 3 over 2, how that connects to 1/2, and all these values look very familiar. And then the t value, the reference number, it sounds a lot like a radian value, which it is, and so it's kind of hard to kind of hold back. But remember that this is an introduction to trigonometry. We haven't really introduced anything about sines, cosines, radians, anything like that. We're simply playing with a unit circle, the distance along the curvature of that unit circle, the ordered pairs along and the ordered pairs along that unit circle. Good. And then starting in the next section, we use that to define what what is a sine and what is a cosine, which is really unsatisfactory as well. I mean, just to ruin the punchline for you, tomorrow when we go back to the unit circle, when we define a point on here, let's say it's a comma b, on the unit circle, say that this is a point on the unit circle, then it must satisfy that a squared plus b squared equals to 1, right? Since this is the unit circle. Unit circle. Spoiler alert, all we're going to do in this direction of introduction to trigonometry is we're going to define the x-coordinate of the value on the unit circle to be cosine, and the y-coordinate of the ordered pair on the unit circle, we're just going to define it to be sine. Just kind of an unsatisfactory definition, I think. So we're just kind of forcing it to be that, without really explaining it, I don't think, in a really clear way. But I think this, coupled with our previous study of sines and cosines, will kind of help bring it all together. Okay, any questions before we sign off?